Hello and welcome to all to this lecture series on basic thermodynamics. This is lecture 5, first law on thermodynamics of thermodynamics continue. Okay, let us begin. First of all, we need to know what is a term that is known as enthalpy. We very much often come up with this term in the analysis of processes in thermodynamics, that is known as enthalpy. Okay, and what is that? We will see. See, during the analysis of process, we very often come across the expression of U plus PV, okay, where this U is the internal energy and this PV is the flow work or displacement work or flow energy. Okay, so for simplicity and convenience, we define this expression as enthalpy. So enthalpy is nothing but this U plus PV, because these are two terms, so we just use a simple term, a single term for both these U plus PV, that is known as enthalpy. It is denoted by H, that is U plus PV. Okay, and it is an extensive property, which means that it is dependent on mass. Okay, it is mass dependent property. Extensive property, intensive property, I have already told you, okay, in the earlier lectures. So when we divide this H, capital H, by small m, that is mass, we get a small h, that is U plus PV by m, which is equal to small u plus p small v. This is the specific internal energy, this is the pressure, and this is the specific volume. And in this small h, this is an intensive property or mass independent property. So this is all about the definition of enthalpy. Okay, let us move. Then heat interaction in various processes. We have seen the work interaction in various processes, the expression for it in the earlier lectures. In this we will see the heat interaction in various processes, how it is defined. See, first of all, we have a process that is known as a constant volume process. The other names are isochoric or isometric processes. I am giving these names because in somewhere while reading some text or while appearing in any exam, you might come across these terms, that is isochoric, isometric process. So at that time you should not get confused, or you should not have a dilemma that about which processes are defined by these terms. So I'm making it very clear. Isochoric, isometric process is constant volume process. Okay, so we have seen that this is the general expression for first law of thermodynamics, that is del Q is equal to du plus del W boundary plus del W other. That means if the volume is constant, that means that the boundary work is 0. So that means that del Q is equal to du plus del W other, or you can also write this du is equal to del Q minus del W other. This is the energy supplied at constant volume, because you see we have seen that we have taken the volume as constant, so del W boundary is 0. So this is the energy supplied at constant volume. Okay, and this is by the definition we have seen, we will get that du is equal to mCv dt. Okay, and for ideal gas, U is a function of temperature only. How this is? For the time being, you just note it in this way, that for ideal gas U is a function of temperature only. When we will talk about the thermodynamic relations in the later part of this course, so at that time we will prove all these things, that U is a function of temperature only for ideal gases. Okay, and what are the conditions to be followed to use the above equation, that du is equal to mCv dt? If the process is a constant volume process, okay, please make a note, if the process is a constant volume process, then for any substance involved, if any substance is involved and the process is a constant volume process, then we have the du is equal to mCv dt. And if the process is ideal gas, then for any process, that means if the substance involved is ideal gas, then for any process, whether it is a constant volume or any other process, we have du is equal to mCv dt. Please make a note, these are very important conditions that for which we use this du is equal to mCv dt. Okay, then we have another process known as constant pressure, isobaric, isopiestic process. Okay, these are also the other names for constant pressure, that is isobaric or isopiestic. This is again the simple statement of first law of thermodynamics. Then we have del Q minus del W other is equal to du plus pdv. This pdv is the boundary work. Okay, and if you write it in this way, you will get del Q minus del W other is equal to dH. Okay, I have told you that this is U plus PV is enthalpy, that is H, so this is DH. Okay, this is the energy supplied at constant pressure. This is how this came. This is by the definition of it. Okay, by the definition that this is the energy supplied at constant pressure. Okay, and DH is equal to mCp dt. Okay, as we have du is equal to mCv dt by the definition, similarly we have dH is equal to mCp dt. And for the ideal gas, H is a function of temperature only. For the time being, you just note it in this way only, and the time in the time later in this lecture series on in this course, we will tell you about that how this H is a function of temperature only for the ideal gas. Okay, we will prove all these relations. Okay, but just for the time being, you just note it in this way that dH is equal to mCp dt, and for the ideal gas, H is a function of temperature only. Okay, and the conditions to use the above equation the same. If the process is a constant pressure process, then for any substance, if the process involved is a constant pressure process, then any substance, for any substance involved, we can use this, the dH is equal to mCp dt. And if we have an ideal gas, so for any process, if the substance involved is ideal gas, then for any process we can use dH is equal to mCp dt. Okay, then we have one very important proof of Cp minus Cv is equal to R for ideal gas. Okay, you might have seen, if you know anything about if you know something about these expression, that Cp minus Cv is equal to R, but please make a note that this is only for the ideal gas. Okay, then H is equal to U plus PV. You know that H is equal to U plus PV, and H is equal to U plus MRT, because this PV can be written as MRT by the ideal gas equation. Okay, and DH, if we differentiate both the sides, we will get DH is equal to DU and MR dt, because this M and R are already constant. And if we write this DH, if we have seen that DH is equal to mCp dt for ideal gas, and DU is equal to mCv dt for ideal gas, and this is MR dt, and if we cancel this dt from throughout and M from throughout, so we will get Cp is equal to Cv plus R, or Cp minus Cv is equal to R. Okay, this is the expression, or this is the proof of that Cp minus Cv is equal to R, but please remember it is only for ideal gas. Okay, and also we know that the ratio of these two specific heats at constant pressure and specific heat at constant volume is equal to gamma, or we see that gamma Cp is equal to gamma into Cv. So by putting this expression for Cp is equal to gamma Cv in this expression, we will have gamma Cv minus Cv is equal to R, and by simplifying we will get Cv is equal to R upon gamma minus 1, and Cp is equal to gamma R upon gamma minus 1. Okay, these are very important expressions. These are used in while solving many numericals in the case of thermodynamics. So please make a note of them, that Cv is equal to R upon gamma minus 1, and Cp is equal to gamma R upon gamma minus 1, and Cp minus Cv is equal to R for ideal gas. And these all expressions are valid only for ideal gas. Okay, and then another process we come across, constant temperature. You might already know that this is also known as isothermal process. So we have that dq is equal to du plus del w. Okay, and del W involves both the boundary work also as well as the other work also. And if the substance is the ideal gas, we know that the du is equal to mCv dt. Okay, so delta Q is equal to mCv dt plus del W, and but dt, if the constant temperature process, for the constant temperature process, the dt will be equal to 0. So in this case the del Q will be equal to del W. Sorry, this means that the net heat transfer is equal to net work transfer for the constant temperature process. Okay, and the change of internal energy is 0. Okay, then for the adiabatic process, you know again that if the process is adiabatic, then heat transfer is 0. That means that du plus del W is equal to 0, or del W is equal to minus du. That means if you supply the work, which means that this del W is positive, means if the work is done by the system, then the internal energy of the system decreases, and if the work is done on the system, that means that del W is negative, so this du will become positive. That means the internal energy of the system keeps on increasing. These are very important expressions. Please note them. Okay, then for the polytropic process, we have del Q plus del U, du plus del W boundary. Okay, and if the system is ideal gas, then we know that del Q, this du can be written as mCv dt or mCv T2 minus T1, and this del W boundary can be written as P1 V1 minus P2 V2 upon n minus 1. This I have already told you in the last lecture. This n minus 1 is for the polytropic process, that PV raised to the power n equal to constant. Okay, and this is the expression for Cv we have used here, that mR upon gamma minus 1 into T2 minus T1 plus this same expression. Then in the We also know that by the ideal gas equation that mRT2 minus T1 can be written as P1 V1 minus P2 V2 upon gamma minus 1 plus P1 V1 minus P2 V2 upon n minus 1. Okay, so when we will use these equations, so we can write it in this form that okay, please make a correction out here that this is this will be P2 V2 minus P1 V1, or you can put a just minus sign out here. This is P1 V1 minus P2 V2 minus P1 V1, because you can see mRT2 that will be P2 V2 and mRT1 that will be P1 V1. So when you will simplify this equation, you will get this in something like this. You will get the Q polytropic is equal to W polytropic, because this is the work polytropic, P1 V1 minus P2 V2 upon n minus 1, and you will get the expression gamma minus n upon gamma minus 1. Okay, this is the very important expression for the polytropic process. And what is the we come across another term that is known as a polytropic specific heat. What is that? See, del Q is equal to mT2 minus T1, and we come across this term. Okay, when we will solve this equation and when we will change in this derivation, we have changed this T2 minus T1 mRT2 minus T1 in terms of pressure and volume. Okay, and but if we need to arrive at this expression, we need to change this in terms of temperature. That is, this can be written as mRT1 minus mRT2, and if we will solve this, we will get this expression that del Q is equal to mT2 minus T1 minus CV gamma minus n upon n minus 1, and this is known as the polytropic specific heat. Okay, please make a note, this term is known as polytropic specific heat, and this is negative because the CV is positive, gamma minus n is positive because n lies between 1 and gamma, so this is positive, and n minus 1 is also n minus 1 is also positive because this lies between 1 and gamma. This is greater than 1, so this is n minus 1 is also positive. This whole term is positive. This means that this minus terms makes it negative. That means the polytropic specific heat is always negative. That means that even when the heat is added to the system, okay, or the energy is added to the system, the temperature of the gas decreases because the work done by the system exceeds the heat supplied to the system. That means that whatever amount of heat you are supplying to the system is doing more work, or more positive work the system is doing, so the internal energy of the system keeps on decreasing. That is why in the polytropic process, the polytropic specific heat is always negative. Okay, that means in spite of providing the heat to the system, the internal energy of the system keeps on decreasing. Okay, because the work done by the gas is more than the heat supplied to the gas. This is very important. Okay, then we have one important expression, that is or the concept that is known as a free expansion. What is it? This is very important to understand. Okay, please understand it very carefully. See, we have a system. Okay, we have this closed boundary system, in which we have insulation all around. That means that the heat transfer cannot take place. Okay, and if in this we make a partition. Okay, we make a partition, and in one side of the partition there is a gas. Okay, you can take it as an ideal gas or any other gas, but we will consider it as an ideal gas. This is an ideal gas. Okay, and this side it is vacuum, and this is just a partition. Okay, just a simple partition. And what happens when we this is the one, we have taken this hole as the boundary 1, and this hole we have taken as the boundary 2. Okay, and what happens when this partition ruptures? Okay, when this partition breaks or this partition ruptures, the gas which is filled in only in this much part of the container, okay, that gets filled in completely. Okay, that gets filled completely. And what happens in this process? What happens that we need to find out. And this kind of an expansion of a gas, where only the gas is contained by some partition, and when that partition ruptures or breaks, the gas gets filled in the entire container. This kind of an expansion of a gas is known as a free expansion. So what are the processes that are involved in this happening? Okay, and what are the changes in whichever properties takes place? Okay, that we will see that we will see how it happens, but this is known as free expansion. Okay, so simple equation, simple first law of thermodynamics tells us that del Q is equal to du plus del W. Okay, and del Q and del W is equal to 0, because I have already told you that this is an adiabatic system, so heat transfer is 0 and there is no work involved in it, because we are not providing any kind of energy, or the system is not doing any kind of work, so the work involved is also 0. That means that the internal energy change in internal energy is 0. That means that the internal energy is conserved. Okay, and we know that the total energy of the system is the sum of internal energy plus the bulk kinetic energy plus the bulk potential energy. Okay, so in this we have seen that U is a constant, or the internal energy is a constant. That means that U initial is equal to U final, and we have already seen if the substance is ideal gas. Because for an ideal gas, this U is a function of temperature only. If the substance is ideal gas, then we can say that T final is equal to T initial, or the temperature final is equal to temperature initial. But what happens? Since the gas develops some kinetic energy at the expense of internal energy, that means when this partition ruptures, the gas flows and fill this entire container. That means the molecules of the gases are acquiring some kinetic energy at the expense of the initial internal energy. That means their internal energy decreases, but after some times what happened? Okay, but after some times what happened, when the molecules becomes stable, means their movement, bulk movement ceases. So at that times what happens, their kinetic energy gets back added back to the substance as internal energy. So the internal energy and the final energy is same. That means the internal energy, initial internal energy and final internal energies are same. That means the initial and final temperature are same, but as the internal energy gets converted into the kinetic energy of the molecules, so the process cannot be considered to be an isothermal process. Okay, the process will not be an isothermal, because the temperature would be, final and initial temperature would be same, but it decreases everywhere in between. Because of that acquire of the kinetic energy by the molecules, the internal energy decreases, and so the temperature decreases. So the process cannot be said as an isothermal process, though the final and initial temperatures and final and initial internal energies are same. That is very important concept, and this is known as free expansion. So make a note of it. And then one more thing is there, that is known as not a free expansion. What is that? See, same condition, volume contained in this half container, okay, fully adiabatic, but in this case, in place of a simple partition, we have created, or we have placed the piston out here. This is a frictionless piston. Okay, so what happens, this if this piston was you can say that this piston was held by some small amount of force which was not allowing this piston to move. Okay, and when that small force is removed, then due to this pressure of this gas, this piston moves. Okay, and this piston moves, so what happens, the kinetic energy of the piston keeps on increasing, because it's a frictionless piston and it is expanding against the vacuum. So there is no friction or no resisting force which can decrease the means there is no dissipative work which the piston has to do against which the piston has to do work. There is no dissipative force because it is expanding against vacuum. Okay, so what happens when this piston starts moving, its kinetic energy keeps on increasing, and the internal energy of the system keeps on decreasing, because the kinetic energy of the piston is acquired by nothing but the internal energy of the gas molecules, because there is no external energy, we are not providing any external energy. Okay, so what happens, and finally when this piston hits the wall, of the container, its kinetic energy decreases, and that energy is again added to the system as an internal energy. So this is the same thing, that the final and initial and final temperature can be same, the final and initial temperature can be same, or the internal energy can be same. Okay, but the process is again not isothermal because the system is losing some internal energy, and because of which the piston is getting some kinetic energy, and at the end when the piston hits the wall of the container, so the energy of the kinetic energy of the piston is again added to the gas. Okay, again added to the gas as the internal energy. So the initial and final internal energies are same. Okay, and the initial and final temperature can also be same if the system, if the substance involved is an ideal gas, but the process will not be isothermal. Okay, so we have shown you here at in a curve of temperature and pressure that this is the initial and this is the final temperature. Okay, and this will not be an isothermal, this will follow this path. Okay, and this cannot follow this path also because the temperature cannot rise, the temperature will only decrease because the internal energy is decreasing, and also the final pressure is less than the initial pressure because we are experiencing expansion. Okay, so this figure will only be like this direction cannot be reversed, and this cannot follow this path. Okay, and if we make a PV diagram, so this is initial, this is final. Okay, I have told you that final pressure will be less because we are experiencing expansion. Okay, and this will be the path because this is an isothermal path. We will not follow this, we will follow this path A because this is and we will not follow this path. Okay, we will not follow this path, we will follow this path because this path is not for isothermal process, this path is for isothermal process, and we know that the temperature will not remain isothermal, it will be somewhat less than isothermal because the temperature will decrease, so we will follow path A. Okay, so this is all about enthalpy and the work interactions and the free expansion and non-free expansion. Okay, in the next lecture we will come up with the open system analysis, and then we will in the further lectures we will move on to the second law of thermodynamics and entropy. Very important concepts coming out in the next lectures, so please stay tuned for those lectures. We will come up with them very soon, and that's all for this lecture. Thank you and have a good day.